Hi, this is Frank Yang from Mr. Knutson's Period 4 class, and today I'll be going over the 2004 AP Calculus AB free response question number 6. Just as a reminder before we get going here, this is a question on the non-calculator portion of the exam. Thus, please put away your calculators when tackling this portion of the test. Now, looking at this problem at a first glance, this problem does not seem too bad, as we have seen material like this before, specifically in sections 9.2 and 9.3 of our textbook regarding slope fields and separation of variables. Keep in mind here that part A is worth 2 points, part B is worth 1 point, and part C is worth a mighty 6 points.
Alright, so let's dig into this problem. So throughout this FRQ, we need to consider a differential equation dy over dx equals x squared times y minus 1. So part A says, on the axes provided, we have to sketch a slope field for the given differential equation at the 12 points indicated. So a good simple first step would be to annotate the problem, as I have done here. Even boxing the differential equation or underlining key elements of the problem will help you gain a better understanding of what you need to solve for. So basically what part A is trying to convey to us is that on those 12 points that they give us, we have to draw their respective slopes on the xy plane. So that's where the differential equation comes in. The differential equation provides us with these rates of change. So here in the middle, I already have the slope fields drawn out. So at first, when I tackled this problem, I looked for patterns. So when I saw the differential equation equal to x squared times y minus 1, immediately what came to mind was that when I plug in 0 into x, 0 squared would be 0, and then that would make the whole differential equation 0, which makes the slope equal to 0. Now we can apply this similar principle to y equals 1. So when you plug in 1 into y, 1 minus 1 would be 0, and then 0 times anything will still be 0. So the slope when y equals 1 would still be 0. So when y equals 1, when x equals 0, the slope is 0. So how about the other points? So for the other slopes, I would use what I call a three-column t-chart. So a three-column t-chart can cohesively organize your x and y values and then produce slopes at the same time. So for example, let's take a point, negative 1, 0. So when you have negative 1, 0, you can plug in negative 1 into x and 0 into y. So negative 1 squared would be 1, and 0 minus 1 would be negative 1. So then when you multiply 1 and negative 1 together, you would get a slope of negative 1. So here, as I've drawn here, at point negative 1, 0, the point has a slope of negative 1. In order to get the full 2 points that we need, for 1 point, you need horizontal slopes when x is equal to 0 and when y is equal to 1. And then the other 1 point came from having positive slopes when y is greater than 1 and when x is not equal to 0, as well as having negative slopes when y is less than 1 and when x is not equal to 0, for a total of 2 points. So as a last tip for all y'all out there, is that not only is it beneficial to annotate the question, but it's also beneficial to annotate your answer. As even simple commentary as having, okay, at negative 1, 2, there's clearly a slope of 1. Or when you have a point of negative 1, 3, there's a slope of 2. So even that can help the reader differentiate between these positive slopes and help the reader know that, okay, this student clearly understands that there are positive slopes when y is greater than 1 and when x is not equal to 0. Okay, so let's delve into part B of this FRQ. So part B says, while the slope field in part A is drawn at only 12 points, it's defined at every point in the xy plane. So in this part of the FRQ, we have to describe all points of the xy plane for which the slopes are positive. So as a good reminder, it is always good to underline or box the key elements of this problem to know what you're solving for. So looking at this from a first glance, this part is actually pretty self-explanatory, as we are applying principles from part A into part B. With the 12 points that they give us, we can clearly see that the positive slopes lie within the regions that I'm outlining with my wand, and we have to look for the commonalities that all these positive slopes have. And therefore, we find that these positive slopes all have 2 commonalities, and that is they all have a y value that is greater than 1 and their x values are not equal to 0. So if your explanation has these two key elements, then you will get this explanation point. Okay, so let's tackle part C of this FRQ. So part C of this FRQ says we have to find a particular solution, y equals f of x, to the given differential equation with the initial condition f of 0 equals 3. So here, I have the original differential equation as stated here. And the first instinct is to go for the technique separation of variables. So while we are conducting this technique separation of variables, we are basically cross-multiplying within this differential equation and then putting the x and dx components on one side and then the y and dy components on one side. So then we can integrate both sides, and then after that we can get this equation, natural log of absolute value of y minus 1 equals 1/3 x cubed plus c. The plus c is necessary because it's a constant integration. We are solving this equation within an indefinite integral, and then we can put a base of e on both sides to get rid of the natural log. The e in the natural log will cancel out, giving us absolute value of y minus 1 equals e to the 1/3 x cubed plus c. Remember, e to the 1/3 x cubed plus c has a power of 1/3 x cubed plus c intact. And then, with careful manipulation of the right side of the equation, we can get e to the 1/3 x cubed times e to the c with the law of exponents. And then here comes the crucial step where we can get rid of the absolute value sign, but at the same time putting this plus or minus e to the c equal to k as a new constant here, because we have the plus or minus e to the c as incorporating both the positive and negative circumstances of the absolute value equation. And then we have e to the plus or minus e to the c transformed as k, because e to the c originally itself is a constant, or can be expressed as a single constant, as e to any constant that's a number will be a constant itself. So once we have this k as a constant, we can clean everything up into a general form equation, and then we can plug in the initial condition into this general form equation to get our k equal to 2, and then we can plug in 2 back into the k, which gives our final solution, y equals 2e to the 1/3 x cubed plus 1. So how to get full points for this FRQ? They reward 1 point for making sure you had the variables y and dy on one side and then x and dx on the other side. 2 points for correctly performing an antiderivative process from here to here. And then 1 point for having the constant integration plus c. And then 1 point for having the initial condition and plugging it in to the general form equation that we solved for. So the general form equation, y equals f of x, has the initial condition plugged in as y equals 3 and x equals 0. And then it awarded 1 more point for solving for y and having the right side of the equation as in the exponential format. As a reminder, you would get a maximum of 3 out of the necessary 6 points for full points if you had no plus c, because even if you had everything right before that, you would still only get 3 points, 1 point from separating the variables correctly and 1 point for antiderivative work, resulting in only 3 points. But an even more tragic mistake would be to not include the separation of variables technique at all, which would result in 0 out of 6 points, which is very devastating. Therefore, a key to remember here is that whenever you have a differential equation dy over dx, it's crucial that you use technique separation of variables, no matter if you're trying to solve for a general solution, y equals f of x, or when you're given initial condition and trying to solve for a particular solution. The separation of variables technique will always come in handy when solving for a differential equation dy over dx.